Hello everyone, today we're going to talk about the orthogonality of spherical harmonics. Now, in my last video, I talked about how we get spherical harmonics, and this is of course a continuation of that video. So now, today, we are going to study the properties of the spherical harmonics and even solve for some ourselves. So let's begin. So here is YML is a spherical harmonic. Just to recap what these harmonics are, the wave function for three-dimensional particle in spherical harmonics R, theta, and phi can be written as a product of two functions, the radial function, big R of R, and the spherical harmonics, y of theta and phi. Now, to find R of R, we have to solve the what we call the radial Schrödinger equation, but y of theta, it's already a given to us. Like we've already solved for what these would be. Now, we know from quantum mechanics that the wave function has to be orthonormal. That is, that the dot product of psi n and psi m has to be the Kronecker delta nm. So for three dimensions, like we have a psi of n lm divided with psi of n prime m prime l prime equals psi of n prime, delta n m prime, delta l prime, and delta m prime. Okay, where n would be the quantum number of the radial wave function. So this implies, since like the total wave function has to be orthonormal, this implies that the radial wave function and the spherical harmonics have to be orthonormal as well. Since if one of these weren't orthonormal, then if you were to take a dot product of the total wave function with another state, you won't get 1 if they're the same and 0 if they differ. So each one has to be orthonormal as well. So orthonormality of the spherical harmonics means that y of ml dotted with y of m prime l prime, it equals delta of m prime and delta of l prime. Let me just remind you, this is just 1 if m equals n, 0. Sorry, if m equals m prime, 0 if m does not equal to m prime, and this is 1 if l equals L prime and 0 if L does not equal to L prime. Okay? So the spherical harmonics have to be orthonormal. And let's test this out ourselves. So let's find y naught naught and y12. And let's check if they are normalized and orthogonal. Which just means orthonormal, right? Now, you may find this problem a bit familiar. This is actually a problem from Griffith's Quantum Mechanics. I strongly recommend that book to anyone that wants to understand quantum mechanics. It's a pretty good one. So yeah, credit to Griffiths for this problem. Let's solve it. So what we do to solve this problem is we first solve for y naught naught. So here's the formula for our general spherical harmonic, and we just plug in m equals 0 and l equals 0 to this. So let's do that. So y naught naught, theta, phi, that's going to equal the square root. Well, l is 0, right? So you have 0 plus 1. So you have 1 over 4 pi. Times, well, now you have 0 minus 0, factorial, that's 1, over 0 plus 0 factorial, which is also 1, e to the naught, so that's just 1, p naught naught of cosine of theta. So this really simplifies down to the square root of 1 over 4 pi p naught naught of cosine of theta. Now we could actually just look up what p naught naught is in a table of the Lagrange functions, but we could also look up what y naught naught is in the table. So I feel like that's kind of cheating. So let's actually solve for it ourselves. So PML, the Lagrange function, is shown here. So let's just plug in 0 and 0. So P naught naught. Oops, you guys can't see that. Here, let's just put that. P naught naught of x is going to equal -1. So I hope you guys can see. So -1 to the m. So that's to the 0 times 1 minus x squared to the m minus 2. That's just m over 2. That's just 0. 0 derivative, which means we don't take the derivative at all of P naught of x. Okay. Now, -1 to the 0, that's just 1. This is 1. This is nothing. No derivative here. I have P naught of x. And P naught of x. Well, P naught of x, here's PL of x. You just plug in 0 here. 0, so 2 to the 0th is 1. 0 factorial is 1. This is holding is 1. 0 derivative, so no derivative at all. All this raised to the 0th power, that's also 1. So this is going to be 1. Which means that P naught naught totally is going to be 1. So you have found the first spherical harmonic. So what do we do next? Well, now we have to check if this is normalized, as in if the dot product between y naught naught and itself equals 1. So let's check. So the integral from 0 to pi, well, double integral, there's a 2 pi of y naught naught complex conjugate, of course. Then it's sine of theta d theta d phi. If you guys are unfamiliar with this over here, this is just the differential in the spherical coordinates system. Okay, so this has to be 1 if it's normalized. So let's just plug y naught naught in and see if this is actually 1. It should be 1. So 0 to 2 pi integral of 0 to pi y naught naught. That's just 1 over square root of 4 pi. That times itself, that's just 1 over 4 pi sine theta d phi. We can move our 1 over 4 pi to the front. Now I have the integral of 0 to 2 pi, so pi sine theta d phi. And this is just 1 over 4 pi times the integral of 0 to pi sine of theta. I'm going to type the integral of 0 to 2 pi of, sine of theta d theta, and the integral from 0 to 2 pi of d phi. Now, what's the integral of sine? Well, if you remember from Calc 1, the integral of sine is minus cosine. So minus cosine of theta from 0 to pi. So, and then times, well, integral of 1 d phi. Well, integral of 1 d phi is just going to be phi, evolved from 0 to 2 pi. Now, remember that the cosine of 0, so the cosine of n pi alternates, right? So the cosine of 0 is 1, cosine of pi is minus, cosine of 2 pi is 1, and so on. So the cosine of pi is going to be minus 1. Well, let's actually carry this out. So you have minus cosine of theta minus cosine of theta, so that's just plus cosine of theta. And then times phi minus phi. But we have to plug in our bounds here. So we plug in pi and 0 here, respectively. So cosine of pi, cosine of 0, and then phi 2 pi, phi 0. Cosine of pi, that's minus 1. So minus 1, that's just 1. Cosine of 0, also 1. So this whole thing is 2. 2 pi minus 0, oh, that's just 2 pi. Okay, so you have 2 times 2 pi, which is just 4 pi. Now note we had a factor of 1 over 4 pi in the front. I forgot to write that down here. So now we have 1 over 4 pi times 4 pi, which is just 1. So yes, the balanced spherical harmonic is indeed normalized. So now let's find the spherical harmonic for y12. So y12 theta phi. This means that m equals 1 and L equals 2. This equals the square root. We just plugging things in. L is going to be 2, so this is going to be 5 over 4 pi. This is going to be 2 minus 1, which is 1 factorial. 1 plus 1 is 2 factorial. Or 1 plus 2 is 3 factorial. 3 factorial is 6. This is just 1 over 6. E to the I phi P12 cosine. I'm going to go a little bit more faster because I feel like this part just plugging things in. So this is going to be square root of 5 over 24 pi. Okay. So P12, again, just plugging things in. So here's PML, P12. So after let's move this up a bit. Really more space. I think that's good. So P12, that's going to be equal to minus 1 to the 1 over x squared, 1/2 d, second derivative actually, of P2 of x. P2 of x is going to be 1 over 2 to 2 is 4, 2 factorial, 2, that's just going to be 2. This whole thing is going to be 8. We're going to have the first derivative, actually. Wait, first or second? Yeah, L is 2. So yeah, so this should be the first derivative, since L is 2. And M is 1. And this should be the second derivative, since L is 2. My bad. X squared minus 1 squared. We expand this out, so this is 1 over 8. Second derivative, right, of x to the 4th plus 1 minus 2x squared. Derivative of x to the 4th is 4x cubed. Derivative of 1 is 0. Derivative of minus 2x squared is going to be minus 4x. Derivative of that again is going to be 12x squared. This is still 0. This is just minus 4 now. And then it's all divided by 8. So this is just going to be, to 12 over 8. 12 over 8 is going to be 3 over 2 x squared minus 1/2. Okay. Oops. Well, we made a slight mistake. Oh, no. There's no mistake. My bad. Okay. Yeah, this is correct. So this is 3 over 2 x squared minus 1/2. So what we do now is we just plug this back into P2 of x. P12 of x equals minus 1 times 1 minus x squared to the 1/2. First derivative of 3 over 2 x squared minus 1/2. This is going to be 0 once you evaluate with this derivative. And this is going to be, 3x once you evaluate with this derivative. So this is just going to be equal to minus 1 times 1 minus x squared to the 1/2, 3x. Okay. Now we plug in cosine of theta for x. So this is minus 1 times 1 minus cosine squared theta to the 1/2 times 3 cosine of theta. Now, if we can recall from trig, this is actually a trig identity. 1 minus cosine squared theta. That's just sine squared theta, right? So now we have the square root of sine squared theta. So the square root of sine squared theta is going to be sine squared. So you have minus 1 times sine theta times 3 cosine theta, or just minus 3 sine theta cosine of theta. That's going to be P12. And then I would just plug that in back into this first part to get that y12. You guys can see that. To get y12 theta phi is going to equal the square root of 5 over 24 pi e to the I phi times minus 3 sine theta cosine of theta. And yeah, we've just found y of 1/2 theta phi. So what do we do now? Well, we have to check if this is we have to check if this is normalized. That's the word for it, normalized. So to do that, let's get a new page because we kind of ran out of space. Get a new page right here. Let's just rewrite what y12 is. y12 theta phi square root 5 over 24 pi e to the I phi times -3 sine theta cosine theta. And so 0, 2 pi, 0 pi, y12 theta phi, y compass conjugate theta phi sine theta d theta d phi. This has to be 1 if it's normalized, right? So let's see if it's going to be 1. What we do is we just plug in y12 into here. 0 to pi, 0 to pi, integral square root of 5 over 24 pi e to the I phi times -3 sine theta cosine of theta. Again, the same thing, but we take the compass conjugate this time, right? So you have square root of 5 over 24 pi e to the minus I phi. This is it's the compass conjugate. -3 sine theta cosine of theta. And then sine theta. This part, sine theta d theta. You guys can see in d. Pretty long integral. So let's simplify this. These are square roots duplicated, so that's just 5 over 24 pi. We can move that to the front, 5 over 24 pi. And we also have a -3 times -3. The minus cancel out, and this just gives us a 6. We can also move the 6 to the front. What's next? I phi, E minus I phi, cross cancels to 1. And we are left with sine theta again, cosine theta again, and sine theta again. So I think I got something on my glasses. But so yeah, sine theta, cosine theta, cosine theta, and sine theta again. So that we have integral of 30 over 24 pi. Integral 0 to pi, integral 0 to pi of, well, now we have a sine squared, right? So sine squared theta, and then cosine squared theta, sine theta right here, d theta d phi. Let's separate this into two parts. 30 over 24 pi times 0 to 2 pi of d phi times integral 0 to pi of sine squared theta, cosine squared theta, of sine theta, d theta. Now, we all know what this integral is going to be. It's trivial. This is going to come out to be 2 pi, right? So what's more interesting is this integral over here. And how can we evaluate? So let me write down this integral on a new page. You have the integral of 0 to pi, sine squared theta, cosine squared theta, sine theta, and d theta. Now, to solve or evaluate this integral, well, what we have to use is u substitution. So let's substitute u, or substitute cosine of theta for u. So use cosine of theta. Oh yeah, and you guys should be familiar with u substitution. I guess that if you're watching a video on quantum mechanics, that you guys should know. If you guys don't know u substitution, I recommend just like watching any video on it. It's a pretty straightforward concept. We substitute u for cosine of theta. This means that du over dx is going to be minus sine of theta. Oops, not du over dx. Du over d theta is minus sine of theta. This means that d theta is going to be minus 1 over sine of theta du. What we can also do is use the trig identity that we used earlier. Rewrite sine squared of theta as 1 minus cosine of theta. So now I have the integral 0 to 2 pi, 1 minus cosine of theta, cosine squared theta, sine theta, d theta. Also, actually, I think there should be 1 over cosine squared. Yeah, 1 over cosine squared. Okay. So what do we do now? Well, yeah, so d theta is minus 1 over sine theta du. So take that. So substitute that with minus 1 over sine of theta du. We see why we chose this. So now this sign goes away, but we pick up a negative. So integral 0 to 2 pi. Well, u is cosine of theta. So this is 1 minus u squared minus that. We have to move the minus to the front. Du, okay? And that's just equals to minus integral of 0 to pi of u squared minus u to the 4th. Just distributing that in. Du, we could break this up into two integrals. Let's go 0 to pi u squared minus 0 to pi u to the 4th, each with the du in the front. Now it's the integral of u squared. That's just going to be 1 over 3 u cubed. Evaluated from 0 to pi, this is going to be 1 over 5 u to the 5th evaluated between 0 and pi. Oops, you guys can't see that. My bad. So, now we put back what we had for u. U is cosine of theta, right? So, put back what we had for u. We have minus 1, 3 cosine theta from 0 to pi minus 1 over 5 cosine, cosine cubed theta, cosine to the 5th theta from 0 to pi. Now again, cosine of pi, that's going to be minus 1. So cosine cubed of theta, that's just minus 1 times minus 1 times minus 1. Oh, actually, let me just expand this out first, so it's going to be more clear if I do that. This is 3 cosine cubed of theta minus 1 over 3 cosine cubed of theta. This entire thing subtracted by 1 over 5 cosine to the 5th of theta minus 1 over 5 cosine to the 5th of theta, and each evaluated with their bounds. So this is going to be cosine of pi, this is going to be cosine of 0, this is going to be cosine pi, this is going to be cosine 0. So what's the cosine of pi? Well, the cosine of pi is going to be minus 1, like I said earlier. So the cosine cubed is minus 1 cubed. Minus 1 times minus 1 is 1 times minus 1 is minus 1. So this is minus 1. This is going to be 1. This is going to be minus 1 times minus 1. That's minus 1, that's minus 1, that's minus 1. 1, 2, 3, 4, 5. Minus 1 times minus 1 is 1. That's 1 is minus 1. 1, minus 1. This is a minus 1. Same thing. Well, this is going to be 1 throughout, right? So now we have minus of minus 1 minus 1 minus minus 1. Oh, my bad. I forgot to put in the constants. This is minus 1 over 3, right? So minus 1 over 3 minus 1 over 3 minus minus 1 over 5 minus 1 over 5. Okay. So this is, of course, going to be minus 2 over 3. So minus is hopefully minus 2 over 3 minus minus 2 over 5. We can finally plug in this minus that we had from the start. So this is going to change your sign here, make this become 2 over 3 plus minus 2 over 5, or just minus 2 over 5. We can then, so this is just going to be 15, just multiply both sides by 5, not by 5. Yes, by 5. 10 over 15. And then this by 3, 15 over 6. Let me get, this is 4 over 15. Alright. Oops. That's 4 over 15. And yeah, wait. Yeah, we are actually done evaluating that integral. I think, let me just make sure I didn't leave anything out. So, yeah, okay. So this entire integral is 4 over 15. So if you can recall, we had 30 over 24 pi times the integral of from 0 to 2 pi d phi, integral from 0 to pi, sine squared theta cosine squared theta sine theta d phi. Now this should have actually been a 45 over 24 pi. Because when I was multiplying 3 by 3, when we were squaring the angular wave function, y12, I accidentally did 3 times 3 equals 6, but it's 3 times 3 is actually 9. That was my bad. I should have paid more attention to that. But, so this should have been a 45 once you factored in that 3 times 3 is 9. This should be a 45. Because, like, we got 30 from doing 6 times 5, right? So 6 should have been a 9, so it should have been 9 times 5, which is 45. So, my bad. So 45 times, yeah, these integrals, we found that this was obviously at 2 pi, and we got that this was 4 over 15, okay? So now, this is just 45 over 24 pi times 2 pi times 4 over 15. The pi's cancel out, and we have 45 over 24 times 8 over 15. And if you were to put this in a calculator, you'd find that this is 1. So y12 is normalized. And now our last question is if they are actually orthogonal. So if they are orthogonal, that means that the integral of both of them dotted together should give us 0. So the integral from 0 pi integral 0 to pi of y naught theta phi and y12 theta phi d, sine theta should be here, d theta d phi, this entire thing, it should give us 0 if these guys are truly orthogonal. Remember that y not, that's 1 over the square, that's the square root of 1 over 4 pi. The square root of 1 over 4 pi. Okay. Times y12, that's the one that we just found. y12 is going to be the square root of 5 over 24 pi times e to the I phi times minus 3 sine theta cosine theta. Now you guys may be worried, this is going to be a very tough integral to evaluate, but not necessarily, and you'll see why in a moment. So let's split this integral into 2 parts. 0 to pi. Really, we could just move this whole thing like to the front. So we're gonna have a square root of 5 over 24 times 4 pi squared in the front. Integral 0, well, times this entire thing. So this, let me just write it again to make it a bit more neater. So we'd have square root of 1 over 4 pi, square root of 5 over 24 pi times this entire thing times the integral from 0 to pi of minus 3 sine theta cosine theta sine theta d theta multiplied by the integral from 0 to 2 pi e to the I phi d phi. But it turns out you only actually have to evaluate what this integral is. So the integral of 0 to 2 pi e to the I phi d phi, well, that's just going to be 1 over I e to the I phi divided from 0 to 2 pi. That's just minus e to the I phi evaluated from, again, 0 to 2 pi. So we have minus e to the I 2 pi minus e, or just plus e to the I times 0, okay, which is just going to be 1, right? So what's e to the I 2 pi? Well, we just use Euler's identity. E to the I 2 pi is going to equal to the cosine of 2 pi plus I sine. Oops, you guys can't see that. My bad. I'll move it up. Sine of 2 pi. Hopefully this works. Sine of 2 pi, that's going to be 0. And cosine of 2 pi, so cosine of 0 is 1. Cosine of pi is minus 1, so cosine of 2 pi is also going to be 1. So this means that this is 1. You have minus 1 plus 1, which is 0. Which means that this integral is going to be, well, 0. So 0 times anything is 0. So this entire thing is 0. So these angular wave functions are orthogonal, and they're both orthonormal. So, yeah, we have just shown that, y naught and y12 are normalized and orthogonal, i.e. orthonormal. So yeah, hope you guys enjoyed this video. If you guys really enjoyed it, please consider sharing it. I really appreciate it. And yeah, that's pretty much it. In my next video, I think I'll be going over the radial wave function, like the radial equation. And after that, we can finally tackle on the amazing hydrogen atom. And maybe from that, we'll go on to helium. I guarantee that. So have an amazing day. Bye.